Welcome everybody at today's high energy colloquium, which is a special colloquium because today we have Richard Bauer, who is the Steve Murray Distinguished Lecturer this week. And Richard is visiting us from Monday until Friday. His office currently is B402, and I circulated the visitor schedule of Richard. So if you want to meet with him, you can still find a slot in his very busy calendar.
No, it's great. It's very exciting having this calendar.
So, Richard is a professor of cosmology at Durham University, and he works at the Institute for Computational Cosmology, where he's trying to create the universe in his computer. There's many processor computers. Right? And Richard is heavily involved in the Eagle simulation, and I believe that we will be hearing a lot from Eagle. So, this means that Richard's research interest is mostly in the observational theoretical studies of galaxy formation. So before he became a professor of cosmology at Durham, he graduated from Oxford in physics. After that, he completed his PhD thesis in Durham. And then he held research positions in Munich and Edinburgh before he returned back to Durham. So today he's going to tell us about black holes, the nemesis of galaxy formation.
Yes, exactly. So today I want to explore an amazing idea that these exotic singularities from general relativity are actually responsible for shaping the observable universe and explaining when you look out at the night sky, galaxies have a characteristic size. And so by trying to understand the role of black holes, we can make a lot of sense about the world we see through telescopes, so try to make as much contact with observations as possible. And then if you come tomorrow, I'll tell you why this determines the future of the universe as well. Okay. So I'm going to be primarily talking about the Eagle project, which is large hydrodynamical simulations of galaxy formation. We solve the laws of physics, including a description for forming stars, for the effects of stars that explode, for the formation of black holes, accretion onto black holes, all the critical ingredients that we need to make a universe. And the exciting thing about the Eagle project is we were really quite successful, I'll show you in the talk, about producing quite a realistic universe. Now, it's good. Why do simulations like this? Well, it's not really a matter of trying to recreate a single universe. It's a matter of if you have a simulation, you can use that as a toolkit to kind of gain more understanding of what's out there and explain the actual universe that you see with a telescope. So I'm very much of the view that these simulations are a tool, and I'll couple them to trying to build simpler models, almost analytic models for the universe, and you can justify the approximations used in those models by reference to the simulations and testing out the simulations. So simulations in this talk are very much a tool. I should highlight various people here. The PI of the project was Job Shea. I'll talk about various students' work, including Stu McAlpine, who's been looking at the role of mergers in the history of the universe. I'll talk about some work tomorrow by Jaime Salcido, and I'll talk about work that's done by John Davies, who's a student with Rob Crane in Liverpool. And it's all very exciting stuff that's still happening. Okay, so let me go through a quick overview of galaxy formation and why it's an interesting problem. So if I plot the stellar mass of galaxies as a function of their abundance, the observational data is this black line here. Okay? And the key thing about this is it's very flat for galaxies smaller than the Milky Way. You go a decade in mass and you get about the same abundance of galaxies. Whereas if you go much bigger than the Milky Way, there's an exponential cutoff. Now, back in the day, we used to think that this cutoff was driven by the fluctuations in the dark matter, the abundance of dark matter halos. But with modern cosmological parameters, you see that there's no discernible break on the kind of scales that we're looking at here. So if I take each dark matter halo, turn it into a galaxy by assuming a constant fraction of the baryons turn into stars, I would predict something like this red line. Okay, a particular realization of that is the blue curve. And the problem is that this, simply putting one galaxy in each dark matter halo, doesn't really describe the galaxy mass function at all. So there's a big difference between how galaxies behave and their dark matter halos. Now we can understand Rees and White, for example, were some of the first people to point out that the reason this is so flat compared to the steep dark matter abundance is because small galaxies here, a single supernova would be enough to remove a large fraction of the material that's trying to form stars. So we kind of have an understanding qualitatively of why this is so flat. But that didn't explain why we have this exponential cutoff, and that's what I want to explore today. Am I going to get muddy fingerprints all over, pizza fingerprints smeared all over the beautiful white screen? Okay, and so the puzzle I want to address today really comes down to what creates that exponential break. And I've kind of given away the punchline of the story is that this is down to black holes. Okay, so that's the background. Black holes are a very exciting possibility for this. There used to, when I was doing my PhD, be a lot of discussion about cooling flows. I think we understand now that black holes are an incredible source of energy that can disturb and heat the intracluster plasma. When that has long cooling times, the energy can often be seen in the forms of these cavities and filled radio bubbles. You can just look at the energetics. You know, for a group size halo, the energy released by building a 10 to the 9 solar mass black hole is comparable to the total thermal energy of the halo. Right? So groups are this incredibly interesting scale. You're dumping from the black hole growth potentially lots of energy disturbing the system like this. Okay. So qualitatively, it seems to make sense that black holes could be very important to the galaxy formation story. But how? Okay. So this is a plot now showing if you compare the abundance of dark matter halos and the abundance of observed galaxies, you can figure out how efficient galaxy formation is in halos of different masses. Okay, so if you go to very small dark matter halos, the fraction of the cosmic baryon content of that halo that forms into stars is only about 1% or even 0.1%, depending on the model. As you go up in halo mass, this increases, okay, until you get to about the mass of the Milky Way, and then as you go more massive than the Milky Way, it comes down again. So that you can infer from observations and your knowledge of dark matter halos. Now the interesting thing is, got to be careful, there's a trap button, is that around here at 10 to the 12 solar masses, an important extra-physical process kicks in. That in smaller halos, cooling is very rapid compared to the dynamical time of the halo. So this means clouds will cool, become very cold and dense and fall to the center. We actually observe this as cold streams flowing to the center, whereas if we go to more massive halos, we're in a situation where the dynamical time of the halo, or the sound crossing of the gas time of the gas in the halo, is comparable to the free fall time, to the cooling time of the halo. So systems out here take much longer to cool than the sound speed. Okay, and this would give rise to cooling flows. Now a simple way of trying to understand this would be just to say, for some reason, black holes can only heat hydrostatic halos. And then that gives you this kind of shape, explains the characteristic scale. Back in 2006, if you make that assumption, you can show that that gives you a reasonably good description of galaxies in the universe. Now, the exciting development to this is to compare this with the Eagle simulation. So the observational data is actually these two gray lines. The results from our Eagle simulations are shown by the different colored lines, blue, green, and red. Okay? And so the simulation, because we've worked on making a simulation until it has this feature to it, does a good job of explaining this basic observational aspect of the universe. Okay, now there are various other things. When we've got the idea of a critical mass in galaxy formation, we can use observations and see how that mass depends on redshift. So in the high redshift universe, is that mass scale about the same? Well, this is data from Peng et al. Showing the mass function, and you see that the transition to the exponential break really doesn't depend on redshift very much at all. And so they're able to reconstruct a picture for how galaxies form in the universe, where galaxies grow more massive, reach around about this transition mass, about 10 to the 3 times 10 to the 10 solar masses, and become passive objects. And they kind of pile up at this point. Okay. Those are called quiescent. If you look at the active star-forming galaxies, you see they become more abundant with time, so that they're much more abundant in the present-day universe than at higher redshifts. But the characteristic maximum mass of a star-forming galaxy doesn't change. And this has been seen in observational data in a variety of ways. For instance, Guinevere Kaufman, looking at the ages of galaxies in the Sloan survey, found a transition mass. Okay, below this mass, objects tend to have young ages. Above this mass, objects tend to have older ages. So there's a very key transition mass scale observed in the universe. And this is what we'd like to explain. Okay, so I've really covered this already. If we look at the Eagle simulation, we get very much that feature. And it evolves in the right way compared to the observational data. So this gives us a great toolkit. If we could understand what happens in the Eagle simulations, presumably we're able to understand as well what's happening in the real universe. So we'd like to go and look in the simulations in more detail, understand the physics, and assume that that then is the physics that happens in the real universe. Now, you shouldn't be too surprised that the Eagle simulations fit this data, okay, because we have the way in which we describe the formation of stars, the feedback from stars, is uncertain. We don't quite understand the behavior of black holes, although I'll show you later, changing many of these assumptions actually doesn't change this transition mass scale very much. Okay. So you shouldn't be too surprised by this, but then having built a model that describes that aspect, we're going to compare the simulation to other data sets. And if the physics is right, we would hopefully discover that we explain other data that are independent of these initial constraints. So we've done this in various ways, looking at intergalactic metals, the evolution of galaxy sizes, looking at the distribution of galaxy colors. These all work reasonably well in the simulation compared to observational data. So it's tremendous. You can make mock catalogs from this that you can compare to observational work. One thing that's important for what follows is we're also predicting the right kind of luminosity distributions for black holes. So if you look at the rate at which black holes are accreting in the simulation at different redshifts, and you compare their abundance to the abundance of observed black holes in X-rays, you find that the simulation is doing reasonably well at that as well. Okay. So I don't think I'm behind. So I can tell you more later about how galaxies evolve in color. You can go and trace back an individual red sequence galaxy and see how its color has evolved with cosmic time. Do this for different gas galaxies. You can learn a lot about interpreting observational data sets in this way. Okay. But what I want to do is I want to take the Eagle simulations and use them as a way of trying to understand more about galaxy formation, and in particular understand what creates that transition mass scale in the properties of galaxies. Okay, so first of all, useful to reinforce that this is the results are very comparable to observational data. So what I have done here, shown in the black contours, are observations from the cosmos optical fields for the growth rates of galaxies as a function of stellar mass. And so there's what's called a blue sequence down here of strongly star-forming galaxies. There's the transition mass scale here, and then galaxies have much longer star formation timescales. Okay, so there's a transition, rapidly growing galaxies that will double their mass on the age of the universe, galaxies that have a time scale for doubling their mass that's much longer. Now, okay, so these contours are the observational data. What's amazing when I made this plot is then I put Eagle galaxies in this diagram, and those are shown as these little dots. Okay, so it's really quite astounding how well the distribution of the dots matches the expected contours inferred from observational data. And this is redshift 1, so this isn't something that was directly related to what we measured locally. Okay, now, the talk, though, was meant to be all about black holes. So what's the significance here? Well, you've seen you've got a blue sequence of galaxies and a red sequence up here, but that's not what the points are colored by. The points are colored by the black hole mass. Okay, so the scale here shows you the black hole mass relative to the halo mass. So actually, these galaxies that are rapidly forming stars have the smallest black holes. And then when I look at the systems that have old ages, they actually have large black holes. It's very interesting that this relationship emerges from the simulation quite so well. Okay. Now, and I should, maybe this is a good point to emphasize, the physics that we put in for black holes doesn't create this transition. Okay. So there's nothing built into the physics that assumes that the accretion or the effects of a small black hole are intrinsically different from the effects of a large black hole. So this transition mass, I'll argue, is occurring from physics related to the ability of halos to cool. Okay, so that was really a very interesting result. You see that any rule is demonstrated by the exceptions, right? So you can go and pick a little galaxy out here that's very high mass and forming a lot of stars. Oh, but actually its black hole isn't that big, so maybe it just for some reason got left behind and didn't understand the game plan of the rest of the galaxies in the universe, right? I've been watching American football, right? So, and these kind of got overexcited early on and ended up being passive when they're perhaps a little bit low mass, so it's interesting, right? So there's not a simple one-size-fits-all model, but there's a general picture here that's very intriguing. So if I plot this the other way, and I plot now the halo mass rather than the stellar mass as a function of black hole mass, it looks somewhat like this. Okay. Now this is quite different to what you would have expected to see, I think, almost everybody I show this plot go, oh, well, shame about that. It was quite an interesting story until you reach this point. But I'll show you observational data later, but the key thing is actually the bit of this that's observed is this, okay, the passive galaxies primarily. If you start pushing to lower mass halos, more actively forming galaxies forming stars, oh, what's the mass of the Milky Way galaxy black hole? It's right down here. Okay, so now, this is a numerical simulation. There are things you have to put in because we don't resolve the full physics, and in particular, we have to start black holes at a particular mass. One of the interesting things that emerges from this is that doesn't actually matter, amazingly. Okay, rapid accretion. Okay, so the story is black holes don't really grow very much. The galaxy grows by forming stars. Then, when we get to this transition mass, suddenly the black hole grows a lot, and then above the transition mass, the black hole grows a bit, but not that much. So that's the sort of behavior that emerges from the simulation. Simulations are horribly complicated, right? And what we'd like to do is to be able to understand it. So let's take a step back and try and construct a simple model. Oh, you need a movie. Okay, before we do that, here's a little movie showing you what actually happens in the simulation. We get the two galaxies you saw there colliding, followed by an explosion that releases lots of energy, tries to heat up the halo around it. It's now created a much bigger halo. Little amounts of accretion onto this object are able to heat the halo, prevent, in the later universe, the incoming material actually ever reaching the center cold. Okay? And so now this is kind of, now in the universe, that's actually a little spiral galaxy with its disk that's not quite ram pressure stripped by the hot halo. This is cooling material in the center that's trying to cool down. A little cooling flow. If you make a plot of what's happening to the black hole, it's making little amounts of growth, but of course a little amount of growth of a 10 to the 8 solar mass black hole is a huge amount of energy. And it's basically able to keep this hot and defend the central galaxy from receiving cold gas from those filaments. Okay, why? That was the key point. So when we ran the first simulations, even the pre-Eagle simulations done by Yetli Rosas Guevara, we discovered that this was an exciting picture that was emerging, but we hadn't a clue why, and we wanted to really understand the physics. Now it turns out that there's important components. One is that actually the black hole accretion rate, which kind of use the Bondi formula. I can tell you, well, at 4 o'clock I'm going to tell people exactly what we do, because we also allow for angular momentum, but essentially the rate of accretion of the black hole depends on the black hole mass squared. And that makes the rate of growth is highly nonlinear, and in fact the black hole will gain an infinite mass in a finite time. Okay? The coefficients here depend on all sorts of subgrid things in the code and on the density of the surrounding material. So, bit of a puzzle why the results don't particularly depend on the details of the simulation, but I'll explain that later. Okay, so this creates a kind of feedback loop. If I have a lot of dense gas around the black hole, I make this number really short, I grow the mass of the black hole, but the accretion rate depends on the black hole mass squared, so it's kind of like a nonlinear switch. Having kicked the black hole into action, even if I let the densities go back, it's going to still accrete and accrete and accrete. Okay. And so here's a little toy model just putting this into practice. The black hole growth is initially very slow, and then it accretes incredibly rapidly. Much greater than exponential. This is already a logarithmic scale. Okay? Notice it's not eventually going to go become an infinite mass black hole, because eventually it'll unbind the whole gas halo and there'll be no hot material around the black hole. But this was a little toy model just to illustrate that nonlinear growth. Okay, I don't want to spend too much time. Okay, but now what's that got to do with this halo mass and the idea that there's a transition in galaxy properties driven by the cooling times of halos? So there are two effects that go on, and I think they simply reinforce each other. One is that if you think about the entropy that you can give to a piece of gas that's sitting in the interstellar medium, wanting to form stars, you could get rid of that gas from the galaxy by giving it a big kick. Okay, and conventionally that's what people have done in simulations, to give things a ballistic kick. But the other way you could get rid of the material is simply to heat it up so that it becomes buoyant compared to the material in the surrounding halo. And then it's just like a hot air balloon. It will just float up into the atmosphere. So maybe this is the difference between a NASA rocket and a weather balloon, right? Now, okay, so that's a very effective way of removing material from the galaxy. So you can imagine in small galaxies, material comes in from the cosmos, it gets heated up in the disk of the galaxy, floats out, very little of it forms into actual stars, if that process is efficient. Now you can work out, well, there's a critical kind of amount of gas that you can heat per star. If you're not heating much gas compared to the amount forming in stars, this outflow mechanism is not a significant factor in the balance. If you turn that into a critical adiabat, you get something like this. Okay, you can go to the paper and follow the details of y to the minus 2/9 and other numbers like that. But essentially, that defines a critical adiabat for material heated by the interstellar medium. And you can compare that to the properties of the halo itself, and you see that two things are going on. One, the halo is getting hotter. So this is the virial temperature of the halo going up, and it's getting slightly less dense, both of which mean that once you're in this regime, this material on this critical adiabat is not buoyant, right? So you've heated it, but it's not going to float. Your balloon no longer works. And so the material stays there, it can cool back down, it will start to just build up more and more interstellar medium in the galaxy, more and more star formation. Or, if that material is transported to the center, it'll turn into feeding the black hole. Okay. So there's two things going on. There's the adiabat of the halo compared to the adiabat of the feedback material. There's also the amount of stuff that can be sustained in that hot corona. It becomes rather large as we go to higher mass halos. So both of those things pick out a particular halo mass, 10 to the 12 solar masses, that doesn't depend on the details of the black hole physics. Okay? The black hole just responds to the build-up of material around it. If supernovae are effective, the black hole density doesn't build up at all. Okay, so you can put that into a simple model now. You can convert that. So rather than this being initially was the growth of a black hole with time, it's now I've turned that into halo mass, because as the black hole over time grows, so does the halo mass grow. I can inject the black hole at a particular mass and watch what happens. I assume that it can't grow more than is required to unbind the halo. Okay, so this gives me a set of curves like this. How does that compare to what happens in the Eagle simulation? Okay, I maybe need to come back to that plot before. Okay, so this dashed line is the prediction of that simple model. I emphasized before that this is the observational data, so normally you would be comparing to black hole masses plotted here. This data comes from Savonen et al. And Alistair Graham and Sandra Svornen already find that there's a downturn in this black hole mass, stellar mass relation. But actually, they're only plotting the bulge masses when they plot stellar masses. I want to focus on the properties of galaxies as a whole. So when you do that, you discover that in this transition mass regime, there's a huge range of black hole masses compared to the observations. Okay, you plot Eagle on this. This is the contours. It's remarkably well described by that very simple model. And you also can color the Eagle galaxies now, and you see that the galaxies that are red are all following close to this extrapolation of from higher masses, but the blue galaxies, the actively star-forming galaxies, lie down here. So it actually is all tying up very well. We can go and say, oh, well, really what I want is a much bigger sample of galaxies. I can go to Volontieri and Rines, who estimate black hole masses based on line widths, and I'll see that they see very much the same kind of behavior. They've colored their dots the wrong way around to make it confusing, but essentially the classical elliptical galaxies sit up here, but you start analyzing AGN out of the Sloan survey, and you find that their black hole masses are coming out significantly lower around this transition mass again. Okay, so why does that work in the simulation? Why doesn't it depend on the physics that describes the black hole accretion? You'd think you'd change that physics, you get a wildly different answer. Well, of course, the point is that the density around the black hole is just the density you need to trigger this nonlinear growth. So if you change the physics of the black hole accretion, you get pretty much the same black hole mass, halo mass relation out. But the thing that does change is the densities you reach in order to get the same growth rate of the black hole. So it's very interesting how the feedback loop optimizes out the actual details of the black hole accretion model. And I said, oh, we always start with black holes of this mass. I'm not sure why. Because if you put black holes in that are smaller, all that happens is they stay small and grow at the same point. Again, what happens, that's this model where I have to reach the highest density to trigger that growth. It's because gas cannot escape from the galaxies. So isn't it wonderful when simulations actually make sense? Right. Okay, now I will be told off if I don't get to the new stuff. So this is my student Stu McAlpine. Okay, he's doing really interesting stuff. The only problem with Stu is he doesn't believe his supervisor, right? So it's a typical student thing that you tell them, well, you know, now what triggers the black hole growth is the halo mass. And we understand that really well. So, of course, Stu goes, well, I'm going to go and find out whether that's true because I've read all of these papers that said mergers are what triggers black hole growth. So Stu went all the way through, did lots of work on the database, found the moment at which the black holes started to grow in this nonlinear phase. I think it turns out that actually typical behavior is very much like this switch. You grow really rapidly. When you average many galaxies together, this trend gets washed out, but it's really strong in individual objects, or at least the ones Stu chose to plot. And it's true in about 95% have clearly identified kind of growth phases like this. You can read the paper for all the details of how you define all these phases. But basically, he then has a time at which the black hole starts to grow in this rapidly growing phase and compares that to when there was a galaxy merger. So basically, he starts at the time of the black hole starting to grow rapidly and looks to see if there was a merger around that time. So we can stack the data. He's plotted this as a function of the dynamical time. So you can combine different redshifts. Turns out that, you know, you'd get the same kind of results if you used the actual time, but this is a cleaner way to combine across redshifts. He also has done a lot of work constructing control samples where you take the galaxies with the same end-day properties and you just pick a random moment and you say, is that random moment also associated with a merger? And there are all sorts of funny biases because, you picked moments early in the history of the universe because that's when there were lots of merging. But you don't see an associated peak. So this is the kind of background merging rate. You see this very strong, well-defined peak showing you that actually a lot of the black holes are associated. And it works out at about 60%. That growth of the nonlinear phase is associated with something like a 10-to-1 galaxy merger. Okay, Stu did also make the plot eventually that shows it's also true that this only happens when the merger is in a 10⁻² solar mass halo. So it's still true what I've told you in the first half. But the point is that what seems to trigger the growth is actually a moment of merger. And maybe I showed you that there were exceptions at the beginning, objects that didn't read the rule book. Presumably those are objects which have not had a merger to trigger this moment of black hole growth. So they might have a lot of gas, but it's angular momentum supported. Okay, so lots of interesting things Stu is doing now. Turns out that this dependence on the dynamical time is quite strongly related to the Eddington ratio. So different sorts of activity, radio galaxies, which maybe are down here in the Eddington ratio, versus quasars up at the top, will have different associations between mergers and the moments of rapid growth. Okay, so currently he's looking at whether this fits with the observations. You can find observational papers which say this is completely wrong, or you can go and read Andy Goulding's latest paper which says this is true and seems to agree quite well with what we find. And a lot of those differences are how you select the AGN. There's a lot of variability which in small samples will wash things out. Okay, so why am I here? Yes, there was a point to this. Okay, so first interesting thing is black holes are cool and maybe shape the universe around us. I find that really interesting. But why I was very keen to come and visit and talk about this was because maybe there's ways to test this looking at the X-ray emission from the diffuse gas that's been heated up by the black hole and potentially moved out of the cluster halo. If we could measure its entropy profiles, how much gas there is in different entropy phases, maybe we could actually learn a lot about what's going on in these systems. Okay, so this is stuff being done by John Davies in Liverpool. He was an undergraduate working for me. I just want to claim some credit for this, right? He's working now with Rob Crane down in Liverpool. And what he's been computing is X-ray emission all the way from galaxies, groups, and clusters to see what the simulations predict, okay, and how much we can learn. Now, to just get to give you a sense of perspective in this, back, years and years ago, in 2012, I couldn't do numerical simulations, so I had to do things the hard way with a semi-analytic model, which is essentially a pen and a piece of paper, and a lot of pieces of paper, really. Now, doing this, you can begin to think about how to make a connection between the galaxy formation properties and what would happen in the halos. And my models then predicted, as you went towards this critical transition mass, remember we'd put this black hole activation in by hand, I think we now understand the physical mechanism, you'd have an increasing abundance of stars in the galaxy, the gas in the galaxy. This is observational data. And the prediction was that the hot gas halo would be getting bigger and bigger and bigger. Suddenly the black hole would turn on, that hot gas would be blown out, and then eventually the potential gravitational potential of a cluster is so big that even a black hole can't resist much. Okay, so again, I was really disappointed, right? This is what happens in ego. So it's very interesting. This is the hot gas content of the halo, right? This is how warm it is. Of course, around 10 to the 12, the gas is hardly ever hot because the virial temperature of the halo is so low. But as you can see, there's no particular spike at around 10 to the 12. There's, as you go up to higher masses, slowly the material is being captured as the gravitational potential increases. And then David is somewhere up there. He's going to have to give you a talk another time about the results from Sea Eagle. Okay, so where we go to full galaxy clusters. So exciting stuff. We can compare this with X-ray observations. So these are from Anderson et al. Versus the stellar mass. You can try and turn those into halo masses, and this is Wang and Anderson are the observational data points. And you can see that very interesting things. You know, Eagle isn't perfect. You know, it's not the real universe, but it captures a lot of these trends. The X-ray luminosities are not scaling like this kind of self-similar scalings we used to talk about. They increase, they're slightly too high. Details of how you do the physics of the AGN feedback seem to make a difference in this regime. And we get closer if we make the AGN feedback more explosive. So something we're working on at the moment is to try and understand that better and to be able to construct very useful models. The other thing is that there's a huge scatter here. So X-ray luminosities of groups and smaller have huge scatters in them, with this being correlated that higher X-ray luminosity is associated with more star formation. And Wang showed me data yesterday, and it's very exciting. It actually agrees with that trend almost completely. Okay, so thank you very much for listening. I hope you are excited about black holes, that they really determine why we live in a galaxy like the Milky Way, why galaxies much bigger than the Milky Way aren't forming stars currently. In fact, they become incredibly rare, this exponential decline. The beauty of this model is it's not just it explains why that transition happens just as the hot halo of the galaxy becomes established, and why that confines the ability of supernovae to drive material outside the galaxy. At that point, the density of gas within the galaxy is going up. Every time you accrete material from the cosmic web, you can't get rid of that material, and eventually something comes along, which is a galaxy merger, and dumps that material onto the black hole, kicks it into a regime of rapid growth, which dumps a lot of energy into the surrounding medium, suppressing, shaping the X-ray properties of that halo. Okay, thank you very much. Okay.
For the excellent talk. So let's see if there are questions.
Wow.
Yeah. So you didn't tell us what you do in Eagle when two galaxies merge. What do you do with the black hole, and how does that influence that turnaround time?
Well, so what we do is that there's a problem of actually tracking the behavior of black holes in small scales because of the limited resolution of the calculations. So the black hole is always being moved to the lowest part of the potential within its kernel. So it may be that as we have two galaxies merging, if the two galaxies have well-defined cores, they keep the black hole within that well-defined core of the galaxy. When that merges and the exact timing of the black hole merger beyond that, I wouldn't trust in these calculations, right? I'd want to do something with much, much higher resolution. But at the same time, the point with Eagle is to try and do a huge box to be representative of the universe. And that's the best I can do at the moment. So it's a limitation. I don't think it will make difference to the details of the timing, but I don't think it has a huge impact.
Other questions?
I think you said that the mergers were important in 40%.
Yeah.
So what about the other 60%?
Yeah, well, it's some ways that it's the exceptions that prove the rule, right? What we suspect in the others is what we count a merger is a ratio of 1 to 10 in the galaxy mass. There will be events with even bigger mass ratios, but we can't reliably classify them to count them as mergers over the whole redshift range of the simulation. So what we think is going on is that you can actually be triggered by really quite a very small mass ratio that doesn't flag in that way of doing the statistics. Okay.
So you had a question?
So the simulation seemed to match the survey data qualitatively nicely in the transition for growth
Yep.
of the critical mass. But it looks like the late type galaxies are maybe a little more massive than the simulations.
Yeah. Well, so one problem is what is the mass of a galaxy, right? So we chose to measure everything in a 30 kiloparsec aperture because that sounded quite big. Maybe we should have chosen 100, and that would have made our galaxies a little bit bigger. But what we really need to do is actually mock up the original data, match the way that you do the background subtraction, and then you'd have a much fairer comparison. So there's a lot of work to do. Now, it's not a surprise in some ways that we are in the right ballpark, right? Because we wouldn't have tried to publish the results if we weren't in the right ballpark, and I want to be quite honest about that. And one of our calibration data sets is that mass function. So we really, we're exploring the parameter space. We now have much better methods to do this, that we're going back and doing it in a much better way. The method we had at that point was not letting Rob Crane go home until he'd found a good set of parameters that kind of fitted the overall shape. So if I was convinced that the observational data were too bright, we would go back and we would change the details of the black hole. Accretion physics does have enough freedom to change exactly where that transition is. So there's some things you should, the fact that that is right within 50%, I could make it fit, right? I want to be quite clear about that, right?
This is a simple one from the point of view of someone who normally looks at stars. Not
Yeah.
galaxies. Your basic, if I follow this, basically what happens is you have a galaxy merger that leads to a very large growth in your black hole, and now you say that star formation has fundamentally changed in your galaxy. You're blaming the black hole. Why not blame the merger?
So the energy comes from, so there's a whole sequence of events, right? So a merger in a low mass halo is not efficient at growing the black hole because star formation can efficiently remove gas and stop it reaching the black hole. So you need the bigger halos with the hot atmosphere around them to make that process that when you try to drive material onto the black hole inefficient, right? So you need the halo. Then we discovered that you also, when you go and look in detail, you find that there is often a merger associated with that moment of growth. So I'm seeing it as kind of this whole big picture that you need, you need everything to be there at once in order for it to work. I don't want to blame one thing above another. I want it to all have a holistic view of galaxies, right?
Okay, Alexei next.
Yeah, so should we compare the CGM properties of Eagle with recent data from UV, cold and gas measurements?
Yeah. So we did some comparisons with oxygen-6, and they work reasonably well. One of the limitations with that is understanding the temperatures of the gas and how the amount of gas corresponds to things like the OV oxygen-6 column density that you might see. And so this was work done by Ben Oppenheimer, and the really interesting result he found was that we matched this trend of passive galaxies having much lower oxygen-6 column densities than actively star-forming ones. And we were really excited. And then we went and looked in a bit more detail. The reason we get that is because passive galaxies are in bigger halos for a given galaxy stellar mass. The oxygen-6 column density is very sensitive to the temperature. And so it kind of comes out right. But it's quite a basic physical thing. So we seem to be doing okay. I wouldn't say we're doing everything perfectly if you look at all the line abundances. One problem is we don't really know the abundances to put into the code from stellar evolution. So you always got a little bit of freedom of how to move that up and down as well. Okay.
Can I ask a second question? Sure. So if we are, let's say, to think about the future X-ray observatory to test some
Yeah.
paradigm.
Yes, please.
So,
Yeah.
which capabilities you would be more
I want to go and look down at the groups and down below the groups down to the actual galaxies themselves. I think this is, to me, the interesting thing. And then once you understand the thermodynamics of the galaxies of the gas in the systems on that scale, then you can begin to understand how you get the entropy profiles of the clusters overall. And when you get David to give you a talk, he'll show you that it doesn't quite work at the moment. The entropy profiles are too hot in the center, too high entropy in the center, too low on the outskirts. And that's what drives those offsets in X-ray luminosity. So there are ideas of what we could do better, and therefore, actually having the observational data would help us understand that much better and help, tie the whole thing into one whole picture of how the evolution of the universe works.
Let me ask a question related to this. So is the entropy profiles more important or the abundance profiles more important? If you could measure only one out to large radii, which is more interesting?
Well, to me, the entropy profiles, because I've written lots of papers about those, and therefore I might pick up more citations like that, right? Interestingly, the abundance profiles seem to work quite well out of the box, but I always have this worry with abundance profiles that how accurately do I know the stellar yields? So I can look at the trends, how steep the gradients are, with some confidence.
So the relative you believe, the absolute?
Yeah, but the absolute, no, I don't believe, right? I mean, I remember going to a conference, this was a long time ago, so it's probably completely unfair, but I'll tell the story anyway, where it was a meeting of cosmologists working on cluster metal profiles and things like that, and galaxy evolution models, and people working on stellar evolution, and the people working on cosmology would say, look, we get these abundances right in clusters and the right dependence on the mass, and so our models must be right. And the people working on the stellar evolution would say, look, we get the abundance right in clusters, so we must be producing the right amount of metals. And it seemed like the two sides were both using the same data to justify whether they were right or not. Right? And I don't know how much the situation has improved. That was quite a long time ago. Yeah.
Okay, sorry.
Hi.
So the black holes only provide bond decrease, is that right?
It's more complicated than that. So it's actually Bondi Littleton Hoyle. So it accounts for the circular speed it accounts for the velocity dispersion. But we've then added another piece to this, that if the gas surrounding the black hole is supported by angular momentum, the accretion rate decreases. Okay, because it.
Cold gas accretion or not?
So it can be both, right? So if it's cold, but angular momentum supported, it doesn't fall in. except due to the viscosity of the system. Now, of course, we don't really know that viscosity parameter, so we stuck a number in like 0.1. But, and the other thing to be aware of is the scales on which we're doing this compared to the, you know, the Schwarzschild radius of the black hole is scary, right? So there's a lot of under the hood stuff that could be done very much better. But our idea was to do something simple that at least, you know, if the stuff was hot, that would suppress the accretion rate. If the stuff was in angular momentum support, that would suppress the accretion rate. So the model achieves those. Obviously, you can do something. If you had resolution of, you know, 10 solar masses, you could do a much better job of this.
Okay, Paul.
So how much does the kind of variability timescale of the black hole accretion matter? Or is it really just the kind of integrated power?
So what matters for the property, for the universe, what the universe cares about is the integrated power, okay? But if we go back and we try to do comparisons to observations, Stu had a paper showing that you get very different results depending on whether you look at black hole luminosity or, you know, some galaxy property and then measure the average black hole luminosities. Because there's a huge orders of magnitude flickering. And now, that comes out of the code. Whether I really believe that flickering at the level we see, I don't know. There could be much more flickering on even smaller time scales than our time step. But the black holes are constantly going up and down in flux. So it's very hard to observe a system and go, oh, that's the power output from that system. It might be a really big black hole running at almost Eddington in a low state, or it might be a teeny black hole pushing up at Eddington for a fraction of a fraction of a million of years. And so we can try to compare things like that to data, how much variability there is at a particular galaxy property, and see how realistic this looks. But ultimately, I'm going to believe what I get out of the observational data.
Okay, if there are no more questions, let me just remind everyone that Richard is here until Friday, so
Yep.
there's still some available time slots on Friday.
Yep.
If you want to meet him,
Yep.
and let's thank him again.
Thank you.